Okay, so for this short section of notes, we're going to be talking about the Carnot engine, which is as close as you can get to ideal. It is the highest efficiency engine possible. But to do that, you've got to have very specific conditions that it undergoes. One is that your transitions are going to be extremely slow. In real life, you're going to get lots of friction and other stuff that mess it up. So this has got to be low friction, very slow transitions where you consider each point basically an equilibrium from the last point. So it's a series of equilibria the whole way along. Even though it's changing, it's slow enough over time that they basically appear the same. And the other one is that because of it, your process has to be reversible. So if I go from A to B, I should be able to go back to B to A and no energy would be lost. Now, real life processes have to be done a lot quicker, and therefore they're not reversible. So a true ideal engine is not possible, but a Carnot engine that's built like this, using slightly faster than ideal transitions is going to give you as close to an ideal engine as you can get. So when we look at our chart over here, here is our PV diagram. We have volume down here. We have pressure over here. So what I've drawn is what a Carnot cycle would look like in real life. Notice these are isothermals. They're along two different temperatures. These are adiabatic. So when we look here, I'm just going to go through each of the steps. In part one, what we have is isothermal expansion. So we're going to stay at our high temperature the whole way. Basically what we've done is there's some amount of heat that's been added to this. We've been holding it still, then we let it go. So now what it wants to do is, since it's warmer than the surrounding area, it wants to expand. It's going to push up on that piston. Now that we've let it done that to where it can still maintain the same temperature, then what we're going to do is we're no longer adding heat, but we're going to allow it to continue to expand until it reaches an equilibrium with the outside air. So we're doing work on the outside, doing work on the outside. This is where we're getting the work from that the engine is going to be pushing along. The next step, and notice that when it adiabatically expands, now its temperature is going to drop because we've no longer added heat, but it's done work, meaning delta U has got to be negative because work is negative and there's no Q. Next, what we've got is isothermal compression. So this is where we're going to close it down, and as we do that, we're keeping it under the same temperature the whole way, so it has to be done relatively slowly. We're squeezing, and we're going to be getting heat out of the engine at this point. And then finally, we have our adiabatic compression, where now that we've compressed it, we've got to allow heat to flow out into the surrounding environment. This would be like our cooling off tank when we talked about the steam engine. So these are going to be our processes for a Carnot engine. Will they be specifically important? No, but understanding how they work is going to be important. We just have a few equations that are going to go along with it. This will be a little more mathematical than the last section. Specifically for Carnot engines, we can, since this is an ideal case, look at some proportionalities that don't work in any other cases. We have that our input heat is going to be proportional to our high temperature, and our waste heat is going to be proportional to our low temperature. So since this is for an ideal engine, what that tells us is that our high temperature minus our low temperature, and take that whole quantity over our high temperature, is going to give us our efficiency. We can rewrite that as just 1 minus your low temperature over your high temperature. So what you see there is that you get more efficient the closer the temperatures get, but remember the work you're getting out of it is going to be proportional to that temperature difference. So the closer you get those temperatures, the less usable work you get out, but the higher temperature difference you get, the more waste energy you're going to use. So based on this up here, we have one last equation that we can use to help figure out low and high temperatures. And it's just because of that proportionality that we wrote up there, where our temperature ratio is going to be proportional to our input and output heat ratios. So this ideal temperature, this is as close as, or this ideal efficiency is as close as you can get to the real thing. When we deal with real stuff, there's going to be friction and other complicating factors. So it's going to be significantly lower than that. And you'll start to notice that efficiencies are not as high as you would have hoped. But that's all we've got to cover on the Carnot engine.